Hello friends, this video on States of Matter Part 16 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched Part 1 to Part 15. See, the first guy who had a complete pressure, volume, temperature for both gaseous and liquid state was Thomas Andrews, and he did for carbon dioxide. And the fact is carbon dioxide behaves like a real gas, right? So he plotted the isotherms where the temperature is constant. I'll explain this graph to you. And why we are studying this graph is because real gas behaves like carbon dioxide. I'll explain. So this was a job done by Thomas, and you observe that 30.98 degrees Celsius, please note degrees Celsius, is the critical temperature of carbon dioxide, because this is the highest temperature at which the liquid carbon dioxide was observed. So if he has maintained the carbon dioxide as 500 degrees, 50 degrees Celsius, he found that the carbon dioxide is always gas. So if he changed the pressure and volume, but this carbon dioxide is always gas. He made it 31.1 degrees Celsius. Still he saw the carbon dioxide, the one on the green line, was always gas. Even if he tweaked the pressure and volume, he found that the carbon dioxide is always gas. The moment he made it 30.98, the one on the blue line, he plotted this kind of graph, and he saw liquid, a small amount of liquid vapors in the liquid state in the carbon dioxide vapors. That means that was a temperature, there was a maximum temperature, highest temperature at which the liquid was coming, or the hydrogen, carbon dioxide was turning into liquid state. And if you decrease the temperature further, he found that he could easily get the liquid state. But above 30.98 degrees Celsius, no chance of getting carbon dioxide in a liquid form, no matter what pressure or volume you put, right? So the maximum value of temperature at which the carbon dioxide is in liquid state was 30.98 degrees Celsius. Above this temperature, carbon dioxide is always gas, no matter what pressure volume you give. You tweak the pressure balance, doesn't matter, it will always be gas. Only if you have temperature below 30.98 degrees Celsius, it will behave like a liquid. And the blue line is the liquid line, the blue area is the liquid area. And he observed good trends here actually. If you see, when he was plotting the graph for this case 21.5 degrees Celsius, he got a graph like this. And after point C, he reduced the pressure further, but the volume was constant. If you see from here, he was reducing the pressure, since I told that pressure is inversely proportional to volume, right? So he was reducing the pressure, the volume was increasing. If you see here, the volume was V3, here the volume is V2. V2 is greater than V3, right? So he was reducing the pressure, the volume was increasing, but at point C, the moment it started becoming liquid carbon dioxide, right? So he was trying to reduce the pressure, the volume increased, but the pressure was constant actually for some time, correct? And then it went down, correct? So also if you see the blue one, so what he did was, let's suppose he was trying to tweak the volume. So he had some volume here, then he decreased the volume a lot, but the pressure was constant. You see, the pressure was constant. So from this point to this point, the pressure was constant. And he further decreased the volume, he saw a change in pressure. Correct? See, from here to here also, if you see this in this fashion, you have some volume. So from here you had some volume. Then he decreased the volume, he saw the pressure drop, but he reached V2. Then he decreased the volume furthermore when we saw a fluid kind of state where we had both gaseous and the liquid state, because fluid is nothing but gas and liquid. We'll explain in the next slide. So he saw that the pressure didn't change. He decreased the volume a lot, but the pressure didn't change. He kept decreasing the pressure, but the volume didn't change, right? And then on further decreasing the volume, he found at a point where then he found that the pressure started decreasing. So let's go back to the critical temperature. We have got 30.98. So at this critical temperature, the volume of 1 mole of the gas at this temperature is called the critical volume, and the pressure at that point is called critical pressure. So if you see, this guy is my critical pressure and this guy is my critical volume. right? Also note that all these critical temperature, critical pressure, critical volume are called critical constant. And as I told, there is a continuity in the aqueous and liquid state. So these are all the blue ones where you see there is a continuity. So the gas also exists, the liquid also exists, both are in the continuous state. So from here to here, for example, you start with some volume and you start with temperature 21.5 degrees Celsius. You start with volume V3, it is in gas state. You make it volume V2, it will be a small liquid will start coming out and the pressure will decrease. You keep decreasing the volume, but you'll see that the pressure won't drop. Only after some point, at let's suppose this point Vx, you'll see that the pressure again start decreasing and it will be in the liquid form then. Correct? So let's understand the fluid. We told the fluid is nothing but a continuous state for liquid and gas. So as I told, there's a continuity between gas and liquid, and that's what my fluid. The term fluid is used either for liquid or gas just to recognize the continuity. To explain the continuity, we use the term called fluid. And liquid can be used as nothing but a very dense gas. And if you see, the liquid and gas can be distinguished only when as I told, the fluid is below critical temperature. If it's above critical temperature, you can't even distinguish. Right? And its pressure and volume lie in the same dome. And in this situation, there is a surface actually which separates that, and they're in equilibrium. There's a surface that separates both these two, and they are two different phases. And in the absence of this surface, there is no way to distinguish the two phases because you can't even actually distinguish. There's a surface kind of thing which distinguishes between these two phases in equilibrium. And once this particular gas is in the critical temperature, the liquid, if you see, that will pass into gaseous state, and the surface will start disappearing. And once you are in the critical temperature and when you apply pressure, you see that the liquid will come up. The gas will be liquefied. So to liquefy the gas, first thing is required is the critical temperature. The gas has to be below critical temperature, and then you have to apply some pressure to make it liquid. Correct? And some critical constant as explained, Tc, Pc and Vc as I explained, right? For some of the gases are mentioned here. For hydrogen, if you see, it's 33.2 Kelvin, pressure is 12.97 bar, and the volume is this much. dm cube is nothing but my liter actually, liter per mole. So these are the values we have for different substances. And we see all these vary a lot. See, the temperature is 33 for hydrogen, for carbon dioxide is 300, for water is 640. So these values vary depending on the type of molecule it is. We'll take some example on this. Says that the gases possess characteristic critical temperature which depends on the magnitude of intermolecular force between the gas. Critical temperature of ammonia and carbon dioxide are given. So critical temperature for ammonia is how much? 405.5 Kelvin, and carbon dioxide is what? 304.10 Kelvin. Right? Which of this gas will liquefy first when you start cooling from 500 Kelvin? So you have 500 Kelvin, you start cooling, the next temperature will come as what? 405 Kelvin. The next temperature will come as what? 304. Correct? And the next you may get 0 Kelvin. This is how you liquefy. 405 Kelvin, what is there? Ammonia is here. And 304 you have carbon dioxide. So if you see, when 405 comes, ammonia will liquefy. Right? Ammonia liquefy. But the carbon dioxide is not liquefied yet because the carbon dioxide will liquefy only when the temperature is below 304. So ammonia will liquefy first. Right? If we start cooling from 500 K. If it is the other way around, you start heating from 0 Kelvin, then you will see first 304 is reached. That means, in fact, both will liquefy. if you start at 0 Kelvin, both will liquefy, because at this point both this will satisfy. We say that the temperature has to be lower than the critical temperature. So the question says you start at 0 Kelvin and you start heating it to 500 Kelvin. Which will liquefy first? It is not carbon dioxide, it is both. Why? Because at 0 Kelvin itself both will liquefy, given that we have proper pressure. Correct? Why? Because at this both are satisfying. Our condition is anything below this. Correct? So if you start from 500 K at 405 K, it will satisfy for the ammonia but won't satisfy for the carbon dioxide. So ammonia will liquefy.
Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.